All right, welcome back to the podcast. Mark here.
And Jenny. Mark, are you ready to dive into the tiny but mighty world of embedded AI processors? Seems like tech that's just everywhere now, but we don't necessarily see it.
Oh, Jenny, fired up is an understatement. This is one of those areas where you see AI not just living in the cloud, but actually getting baked right into the devices we use every day. And the market numbers. Whew, oh man, they tell a pretty compelling story.
Lay it on me, tech guru. What's the buzz? Is it just more growth, or are we seeing a shift?
Okay, so buckle up. The global embedded AI processors market is projected to go from $3.7 billion in 2024 to a little over $6.15 billion by 2030. That's a solid 8.6% compound annual growth rate. But here's the kicker. Some reports looking at the broader embedded AI landscape, including things like sensors and modules, are seeing CAGRs closer to 14%. So it's not just processors, but the whole surrounding ecosystem that's expanding quickly.
Wait, why the difference in numbers? Is it just about how you define embedded AI? Like, is it just the chip, or is it the whole package?
Exactly. It's the scope. Our core research is focused on the processors themselves, the actual silicon doing the AI heavy lifting. The broader numbers are pulling in the whole ecosystem. The tiny chips, yes, but also the software that runs on them, the integrated modules, even the services built around them. It's the difference between counting just the engine of a car versus counting the engine, the transmission, the dashboard computer, the whole smart system. But either way you slice it, it's significant growth. We're talking billions and billions of dollars.
Okay, that clarifies it. So, it's growing fast. Where are we seeing these processors show up? What are the big applications everyone's excited about?
Oh, it's everywhere. Data centers, obviously, using these specialized chips for machine learning to handle massive amounts of data. But the exciting stuff, the real interesting transformation, is happening at the edge. That means AI moving out of big server farms and into actual devices. We're talking autonomous vehicles, sophisticated medical devices, and this is huge. Industrial automation. Our data points to industrial automation being a $3 billion plus opportunity. Think factories becoming truly smart.
Industrial automation? Like robots in factories getting smarter than just doing one repetitive task?
Precisely. Think about factories needing to do predictive maintenance on machines, identifying a potential issue before it causes a costly breakdown, or having robots that can adapt to slightly different parts on an assembly line, making decisions without sending everything back to a central server or a human operator. Embedded AI processors let them do that processing right there on the factory floor. It cuts down on latency, makes things more reliable, and frankly, makes the factory way more efficient.
That makes sense. Reducing that dependency on constant cloud connectivity seems key for things that need to react in real time, like, say, a self-driving car, right? You can't wait for data to travel to the cloud and back when you're navigating complex traffic.
100%. Autonomous vehicles are massively reliant on embedded AI processors to crunch data from sensors, the cameras, the LiDAR, the radar, fast enough to make split-second decisions. No time to call home to the cloud when you're navigating city streets. And it's not just big players like NVIDIA with their Orin socks that power level 4 autonomy. It's also happening in smaller devices, enabling more basic levels of driver assistance and safety features in regular cars.
Like what else? My smartwatch suddenly getting smarter? Maybe understanding my health data better?
Well, yeah. Medical devices are a big area. Think about wearable health monitors or even implants. They need embedded AI that's incredibly energy efficient. We saw research on analog-first ML chips, potentially reducing power consumption down to microwatts. Why? Because a wearable needs to last for months, maybe even years, on a single charge. You don't want to charge your glucose monitor or your pacemaker every night. That energy efficiency is critical, not just for convenience, but for patient safety and comfort.
That's a good point. Energy efficiency is a huge differentiator, especially in devices that are literally attached to you. Speaking of chips, we hear a lot about different types: ASICs, FPGAs, AI accelerators. Can we break those down a bit? It can get a little jargon heavy.
Absolutely. Think of it like tools in a toolbox, each designed for a specific job or level of flexibility. An asterisk times asterisk, or application-specific integrated circuit, is like a specialized tool. Say, a custom wrench built for one specific bolt size. It's built for one job, and it does that job incredibly well and efficiently. High performance, super low power consumption for that task, but you can't use it for anything else. Great. Great for mass-produced devices with a fixed, well-defined function, like a chip, dedicated to a very specific part of a camera's image processing.
Okay, custom wrench. Got it. Very focused.
Then you have times FPGAs, field programmable gate arrays. These are more like a multi-tool or a reconfigurable breadboard. You can reconfigure their internal connections and logic to do different things, even after they've been manufactured and deployed. They offer flexibility if your algorithm might change later, or you need adaptability for different tasks. An FPGA is often the way to go. Professor Anil Jain from Michigan State mentioned exactly this: how FPGAs are beneficial when you need to adapt or update machine learning models post-deployment, without having to redesign the hardware from scratch.
So flexibility and adaptability versus pure, optimized performance?
Exactly. It's a trade-off based on the application. Then you have times AI accelerators times asterisk. These are a broader category, including things like TPUs, tensor processing units developed by Google, or specialized cores within larger processors. These aren't general-purpose chips like a CPU. They are specifically designed to speed up the complex calculations involved in machine learning, things like matrix multiplications. Think of them as engines built just for running AI models fast and efficiently, especially at the edge, to reduce latency and enable faster responses.
Okay, the AI workhorses, designed specifically for the heavy lifting of neural networks.
Yep. They complement CPUs or other processors by offloading those specific AI tasks. And finally, times DSPs times asterisk, digital signal processors. These have been around for ages, optimized for processing digital signals, like audio or video streams. They are still useful in embedded AI for things like pre-processing sensor data, cleaning up noisy signals before they hit the main AI processor, or handling simple audio commands before more complex natural language processing is needed.
That helps a lot. So we've got different tools for different AI jobs at the embedded level, each with its own strengths. Who are the companies making these tools? Is it the same big names we always hear in the chip industry?
The usual suspects are definitely in the mix and continue to be major players. NVIDIA continues to be a powerhouse, especially in AI accelerators for data centers and high-end embedded applications like autonomous driving. Their chips are the backbone of a lot of serious AI work. Qualcomm is strong in edge devices, particularly in mobile and related areas, focusing on bringing AI processing closer to the user on phones, smart home devices, and even into industrial IoT. Intel and AMD are also significant players, offering a range of processors and increasingly integrating AI capabilities into their lineups, from powerful server chips down to more embedded-focused solutions.
And it's not just the giants, right? There are other companies making waves, maybe specializing in specific niches?
Definitely. Companies like Renesas and Texas Instruments are key in industrial and automotive embedded systems, and they're rapidly integrating AI features into their microcontrollers and processors to meet the demands of those markets. And then you have interesting startups, often focusing on new architectures or very specific AI tasks, like those working with RISC-V architecture, which is a big future trend we should talk about. It's causing a bit of a stir.
RISC-V. I've heard that term pop up more and more, especially in the news about chip design. What's the deal with it? Why is it significant?
Oh, RISC-V is fascinating, and it has the potential to change the landscape quite a bit. It's an open-source instruction set architecture. Think of an instruction set as the fundamental language a processor understands, the basic commands it can execute. Most instruction sets, like ARM or x86 dominant in PCs and mobile, are proprietary, requiring companies to pay licensing fees to use them. RISC-V is open. This means anyone can design and build chips based on it without paying those often significant licensing fees. This is huge for innovation and accessibility.
So, lower costs and more freedom for designers and smaller companies?
Exactly. It lowers the barrier to entry. It fosters innovation and customization, because companies can design processors specifically tailored for their embedded AI needs, maybe focusing on extreme energy efficiency or specific types of AI calculations, without being tied to a single vendor's roadmap or licensing costs. Some projections suggest RISC-V could capture a significant chunk of the automotive microcontroller market post-2026, which is a testament to its growing traction. Companies like Tenstorrent and Aspinity are leveraging this open approach to create specialized AI chips with unique capabilities.
That could disrupt the market quite a bit, introducing more players and more specialized hardware. What about the other big trend you mentioned, Edge AI?
Edge AI is the shift to doing more and more AI processing directly on the device itself, the edge of the network, instead of sending all the data to a central cloud server for processing and then sending results back. This is critical for low latency, as we discussed with autonomous vehicles. If a factory robot had to send every sensor reading to the cloud for analysis before deciding where to place a part, the assembly line would grind to a halt. It needs to react instantly. Edge AI reduces that communication delay significantly.
And it has implications for privacy too, I guess? Less sensitive data being sent off-device to some remote server?
Precisely. Doing computation locally can significantly enhance privacy, because the raw, potentially sensitive data, like images from a security camera or health data from a wearable, stays on the device and isn't transmitted over the internet to a third-party cloud service. However, this also raises questions about security on the device itself. How do you ensure the AI on the device isn't compromised? And there's the complex regulatory oversight, especially in places like the EU, where data privacy is a significant concern. It's a balancing act between performance, privacy, and security.
Okay, so growth, different types of chips serving different purposes, big established players, and emerging architectures like RISC-V challenging the status quo, a significant shift to edge AI for speed and privacy, while also bringing up security and ethical questions. It sounds like a really dynamic, maybe even a bit Wild West, space right now. Any other cool future tech on the horizon that we should be keeping an eye on?
There's definitely a lot of interesting stuff brewing in R&D labs. For instance, there's considerable buzz around neuromorphic computing. These are experimental chips fundamentally designed to mimic the structure and function of biological brains. Using spiking neural networks, they potentially offer incredible energy efficiency and processing power for certain AI tasks that are well suited to that architecture. Intel Labs has prototypes showing promise in things like analyzing complex signals, like EEG signals, with ultra-low power consumption, which could be huge for future medical wearables or brain-computer interfaces.
Chips that think, or at least process information, more like brains. Wild. Okay, so to sum it up, the embedded AI processors market is growing fast, driven by demand in industries like automotive, industrial automation, and healthcare. There are different types of processors optimized for different needs, from pure speed with ASICs and accelerators to flexibility with FPGAs. Key players are pushing innovation, and open architectures like RISC-V are gaining ground, potentially democratizing chip design. All of this is driving a significant shift towards processing data and running AI models directly at the edge, which reduces latency and can enhance privacy, though it also brings up important security and ethical considerations. Did I miss anything in that whirlwind tour?
That's a solid summary, Jenny. You covered the key points really well. It's a market that is quietly but steadily embedding AI into more and more aspects of our lives, making everyday devices smarter, more efficient, more capable of autonomous operation. Definitely a space to keep watching. It's evolving quickly.
Absolutely. And it makes you think about what the average toaster or doorknob might be capable of in a few years. Thanks for breaking that down, Mark. It's fascinating stuff.
My pleasure. Always interesting to look under the hood of the technology shaping our world. And to our listeners, thank you for joining us for this deep dive into embedded AI processors. We hope it gave you some insight into this growing market.
Thanks for listening. We'll catch you next time for another look at the tech and trends driving the future.